All right, so again, this is 11.6, number 8. All right. And again, I'm going to give you all time to work through this as well, so it's not just me yapping the whole time. So here is our problem. All right. We're given this function of x and y, that is x over x squared plus y squared. Right? And just to kind of remind us on what we're doing on these things, we want to find, the directional derivative. Right? So that's something we'll need to find. Right? And we want to find it in the direction of some vector that we're given v. Right? And in this case, the direction that we're given here for v is that vector 3, 5. Okay. All right, so just to remind us on what we're trying to do here, if you have your book, again, if you want to flip maybe over to page or flip back to page 661, right, that's where we start talking about directional derivatives. Right? So here's the formula that we were working through in class. Right? It looks something like this thing. Right? This stands for the directional derivative in the direction of u, where, if you remember, u is a unit vector. Right? So what we're going to have to do at some point is take this vector v and turn it into a unit vector. Right? So this directional derivative is just the gradient of our function f, right, dotted with this unit vector. Okay? So this is what we will have to know in order to answer this type of a question. Okay? All right, so let's just start walking ourselves through this thing. For the gradient part of it, just to remind ourselves, and again, unmute yourselves so we can talk about it as well. Do you all remember what the gradient of f represents? In this case, we have a function of f that has two variables. So what does my gradient of f look like? You guys remember this stuff? Yeah, you bet. It returns a vector, and each of the components are those respected partial derivatives, right? So in this case, since we have two variables in here, it'll be a component where the first partial is with respect to x, the second partial is with respect to y. Right? If we had three variables in there, we'd have a third component where the partial would be with respect to z or whatever variables we happen to be using. Okay. All right. So for this one, let me see. Well, I'll go ahead and do this one for you because we're going to do another gradient problem in a little bit where you have to work on it. But here's the partial with respect to x. And again, go back later when we get done and just verify this just to make sure you all can do it as well. But I've got y squared minus x squared over the quantity x squared plus y squared squared. Right? Because for that partial, I've got x's in the top and bottom, so I have to use my quotient rule. Right? For the second component, since I'm taking that derivative with respect to y, that's just the same thing as x times x squared plus y squared to the minus 1. Right? So that's just a constant, so I can leave that alone. And then the derivative of this thing is negative 1 times x squared plus y squared to the minus 2. And then the partial of this with respect to y is just 2y. Right? So if you multiply all this stuff together, you get a negative 2xy up top and x squared plus y squared in my denominator. Right? So there's our partial, right? At least for y and for x. So that leads us to the gradient. Right? All right, so we've got this part of the problem done now. Well, almost. We have to do one other thing, and let me see. I don't think I wrote it down, but the point that we are using in this problem is the point 1, 2. Right? So what we'll do is we'll take these values 1 and 2 and plug them in here when we start to evaluate it. Okay? All right, so now let's figure out what u is. So if v is this vector, 3, 5, how do I turn that into a unit vector again? What do we need to do? Yes, ma'am. Right. So for this case, the distance is just the square root of 3 squared plus 5 squared. So that's the square root of 9 plus 25, or the square root of 34. So u will just be 3 over the square root of 34 and 5 over the square root of 34. Okay, excellent. So now what we need to do to get my directional derivative is to take my gradient, evaluate it at the point, and then take the dot product of that with u, where we just found. Okay. So let me figure this thing out over here. Okay. So if I plug 1 in for x and 2 in for y, again, check it to see if you all get the same thing when you rework it, but I think I get a 3 over 25 and a negative 4 over 25. Right. So down here I will take that vector dotted with u, right? And then remember, if we take the dot product, we just multiply those together, and add them up. So that looks like it's 9 over 25 times the square root of 34, and negative 20 over 25 times the square root of 34. So they've got the same denominator, so I can just add those things together to give me this value. Okay. So there's my directional derivative evaluated at the point 1, 2 in the direction of 3, 5. Okay. All right. So any questions or any concerns you have about this one, other than just trying to remember what we were doing 3 months ago or so? All right. So anything then on 11.6, at least number 8? All right, so when you're reviewing for this stuff, if you want to just go over some more, you can always shoot them off to me in an email. We can get together and we can look at more. Okay, but let's move on. Well, and by moving on, I mean actually moving back. Right. What I want to do next is talk about tangent planes. Right. That's the next one. That's VF3. Right. I'm not going to go over VF1 very much because you guys can do that. Right. That's just plotting points and vectors. It's all that introductory stuff we were doing back in chapter 10. Okay. So in 11.4, that's where we started talking about tangent planes and linear approximations. We really mostly focused on tangent planes, so let's just worry about that stuff. Okay. So in 11.4, here's number 4. Okay. I've got this equation, z equals x e to the xy. Right? And what I want to do back here in 11.4, let me make sure I'm reading it to you right. Oops. There we go. Yeah, all I want to do is find an equation of the tangent plane to this surface at the point 2, 0, 2. Right? And I know that point's on the function, right? Because if I plug 2 in for x and 0 in for y, I do get 2 for z. So at least I know it's on there. Right? So if you have your book, flip over to page 642. Right? That's where we see the equation we need to use for this thing. Right? So for here, the equation for this tangent plane, if we're given this particular setup, is z minus z naught is the partial of x times x minus x naught plus the partial of y times y minus y naught, where again these partials are evaluated at this point. Right? So in this case, it would be the partial of x where I plug in 2 for x and 0 for y to get that number. And do the same thing for the partial of y. Plug in 2 for x, 0 for y, get that constant, and then multiply it by y minus y naught. Okay. All right, so I'm going to ask you guys to pull out some paper. So just so you all can practice this, find the partial with respect to x, and I'll find the partial with respect to y. Right? And it shouldn't take too long. I'll give you just a minute or so to get that thing. All right, anybody come up with that partial for x? Perfect. You bet. Good job. Thank you. Yeah, because on that one we actually have to use our product rule to get our derivative. All right. So again, what we want to do to get these parts is to take our point and plug them into our partial. Right. So let's take that partial of x and evaluate it when x is 2 and y is 0. Right. So that just gives me e to the 0 plus 0, right, which is 1. And then over here, if you plug in 2 and 0, we get 4 times 1, which gives me 4. Right. So then if we just throw this into our equation for this tangent plane, it'll be z minus its point, right? So in this case, z minus 2. And that equals this derivative evaluated at 2, 0, which was 1, times x minus its value, plus the derivative of y evaluated at this point, times y minus 0. Right? So in this case, I've got z minus 2 is just x minus 2 plus 4y. And then if I take that 2 over to the other side, you just get z equals x plus 4y. So there's the equation for that particular tangent plane. Okay. All right, so again, if we're given a function and a point like this, then we can jump out to this style of getting my tangent planes. Right. Do you all remember how we were doing these things back in chapter 10? What we had to have in order to find the equation for a tangent plane? So if I gave you some type of a plane right here, what did we need in order to find the equation for that plane? A direction vector. And what was the direction we had to use? Does that help? Remember, we needed a normal vector, right, and some type of a point in the plane. And if we had these two things, then we could find the equation for that plane. Right? Because remember, if I just gave you a point, I could rotate that plane all the way around that point, or rotate a plane all the way around that point. But the normal vector kind of fixes it and holds it in place for me. Right? So you might want to go back and just review that, because one of the things we did, and again, it goes back to the chapter 10 stuff, how do you find a vector that's normal to a plane? What can you do? I wonder if this will help. Remember, if A and B are in the plane, what does A cross B return for me? Well, if A and B are vectors and their cross product, remember, it returns a vector. And what was another important property about that vector that was returned? Here's kind of a hint right there. Correct. It's perpendicular, right? Which is what we would need. Right? So if I give you two vectors in the plane, I could take their cross product to get this normal vector, and then pick some point in the plane to finish it off. All right, but going back to section 11.4 there, number 4, any questions on how we used this formula to get the equation for the plane? All right, let's look at a couple more then, just to kind of get us going for at least starting our review. If you want to flip your book over to section 11.5 now, this is where we talk a little bit about the chain rule. And here's where the chain rule kind of comes into play. Let's say I have, this is number 18 in the book. Let's say I have this function t that's a function of v and u. But I know that u is a function of p, q, and r, and v is also a function of p, q, and r. Right? So normally when we're given something like this, I could find the derivative of t with respect to v, or the derivative of t with respect to u, just by using the partial stuff we've been doing for a while. Right? But now what happens if I want to find the derivative of t maybe with respect to t, or p, or the derivative of t with respect to r, or the derivative of t with respect to q? Right? This is when we have to start using the chain rule to help us find all these different partials we have to kind of combine together. Right? And the way we at least tried to help us visualize it is we made what was called this tree, right, where we talked about each functions and their variables, where t was a function of u and v, but u was a function of p, q, and r, and v was a function of p, q, and r. So if I want to find the derivative of t with respect to one of these subvariables, we kind of have to go down this tree to see all the different partials we have to find. Right? So for instance, if I wanted the derivative of t with respect to q, what I would do is I would start here at t and find all these different partials that led to q. Right? So there's one and there's one. Right? So to find this total derivative of t with respect to q, I would find all these different partials, right? So for this one, that's the derivative of t with respect to u, and then this part of the tree was the derivative of u with respect to q, and then for the second one, it was the derivative of t with respect to v, and then the derivative of v with respect to q. So we found all the ways to get from t to q and wrote down all those different possibilities for my total derivative of t with respect to q. All right, so you all good with how we've done this stuff so far? At least how we set up our chain rule. And again, you really need to use this when you have variables within variables, kind of like this thing. If we were just given this and asked to find the partial of t with respect to v or u, don't need to do any of this stuff, right? Just a regular old type of a problem. Okay. All right, so here's what we want to find. Let's find we got it set up. So let's say the derivative of t with respect to q when, how about p equals 2, q equals 1, and r equals 4. Okay. Of course, we're going to need these at some point. So what happens if I take these points and kind of plug them back in up here to get u and v? Well, u would be p times q times the square root of r, and v would be p times the square root of q times r, which gives me 8. Okay. All right. So remember, you don't want to actually plug in values until you actually take your derivative. Otherwise, when you start taking derivatives, your constants will go to 0. So let's figure out what this thing looks like, and then we will evaluate it with these numbers we've come up with. Right? So the derivative of t with respect to q. Okay. All right. First of all, what's my derivative of t with respect to u? In other words, what's this first part? Well, let's go back up here at t and find its derivative with respect to u. Right? So in this case, if I have v over 2u plus v, since u is my variable here, v is just going to be a constant. Right? So I could rewrite it like this thing. And then when I take the derivative, I can leave that v alone. And then if I use my chain rule on this, I'll get negative 1 times 2u plus v to the minus 2. And the derivative of this with respect to u is just a 2. Right? So it looks like I've got a negative 2v up top and 2u plus v squared in the denominator. So that is the derivative of t with respect to u. Right? Now let's find this thing, the derivative of u with respect to q. Right? And here, u is p times q times the square root of r. So in this case, p and the square root of r are just constants, and then the derivative of q is just 1. Right? So then this will be times p times the square root of r. Okay? All right, and then to finish it off, let's do the second half of this. All right, so let's find this part. All right, so again, t here is v over 2u plus v. So since I have variables up here and up here, let's use my my quotient rule to get my derivative. So it'd be the derivative of the top times the bottom minus the top. And the derivative of the bottom with respect to v is just 1. And then that's all over my denominator squared. Right? So that's 2u plus v minus v over 2u plus v squared. So those add up to 0, and I'm left with a 2u over 2u plus v squared. Okay. And then that's times the derivative of v with respect to q. So let me clear off a little space here. So in this case, v is p times the square root of q times r. So if I take the derivative of v with respect to q, p and r are constants. And then for q to the 1/2, that would be 1/2 times q to the minus 1/2. So it looks like this will just be p times r over 2 times the square root of q. Okay. All right, so that is my derivative. Okay. Now we're asked to evaluate it at, what point was it? Oh, at this point right here. Oh, just kidding, didn't mean to erase it. Okay. Supposed to evaluate at this point right here. So if I plug in those values for p, q, r, u, and v and add all of those together, again, go back and do the work and check and see it, but I've got 1 over 32 for this. Okay. All right, so that's number 18, right, from section 11.5, just a quick review of our chain rule. Any questions about how we set up any of that or how we found those derivatives, evaluated it, did any of that stuff? Are you all okay with it? Okay, well, let's just do one more here just to kind of review the first part of our material. Let's do a Lagrange multiplier problem. Okay. So let's go to section 11.8, right? And here's number 10. So I am given this function, f of x, y, and z equals this. Right? And I'm given this restraint that x squared plus y squared plus z squared equals 1. Okay. All right. So let's think about some things. First of all, let's look at that function f for a second. If I ignored this constraint for a minute, whenever I find critical points for f, do you think those would be like an absolute max or an absolute min? What do you think? Just by looking at how f is set up. Do you think you can find an absolute for f just by looking at f? Do you think when we find our critical points and plug them in, we get a number, and then we have to try to justify, is that number a max or a min? So if you look at f, with, again, ignore the constraint here for a little bit, but if you just look at f, do you think you can find an absolute max or an absolute min of f just all by itself? Well, I was just thinking, if you just look at the function of f, can you have an absolute max or an absolute min for f? For instance, if you look at f, what's something you know it's never going to be? If I take x to the fourth plus y to the fourth plus z to the fourth. Yeah, it definitely can't be negative, but what if I plugged in the 0.000? What do you get? Yeah, then you do get 0, right? So it can't be negative. It could be 0. But then if you look at x to the fourth plus y to the fourth, we could make that thing huge, right? I mean, I could plug in a billion for x and a gajillion for y. So we can make that function as huge as it can go on to, right? There's no way to actually get a maximum value for it, right? So if you just look at f all by itself, we can find an absolute minimum, but there's no way to get an absolute maximum for it. Okay. All right. So now, what happens if we throw in this constraint that we've got right here? Well, we still could have an absolute max or an absolute min, but now we might actually have an absolute max as well. Right? So if you remember, the way we found this is we found all the possible critical points. And then once we found all those possible critical points, what we did was we just plugged them into our original function. Right? And then the largest value was our absolute max, and the smallest was the absolute min. Right? And that's our strategy for this thing. Right? So then I guess the next question is, how do you find all your possible critical points? Well, this is where the Lagrange multipliers came into play. Right? We saw that we could find our critical points whenever the gradient of f was equal to lambda times the gradient of g, right, where g was this restriction. Okay, so what we're going to do is we're going to kind of walk through this thing. We're going to set up this equation. Right? We're going to think about all the different constraints we might have on this particular problem, use that to get a list of every possible critical point we can get, and then once we have that list set up, we'll just plug them all into f to see where we get our biggest and smallest values. Okay. All right, so that's the strategy for using these Lagrange multipliers to get our maximum and minimum values. All right. So before we actually start going through that, any questions on our strategy and what we're going to be doing? All right. Well, take a second and see if you can remind yourselves how to do this step. All right. Just do that first step for me. Don't try to solve anything just yet. Just set it up for me as I kind of erase this and get stuff ready to go. All right, and it's really not that bad, right? Because what's the gradient of f? That's the gradient of g, right? That's okay. So the gradient of f, it's the same idea though, right? You just take those partials with respect to x, y, and z, right? And we want to set that equal to the gradient of g, which was 2x, 2y times z times lambda. Right? So this is the system that we have set up to try to find all our possible critical points. Okay? And if you set all these components equal to each other, that just tells me that 4x cubed has to be 2 lambda x, 4y cubed has to be 2 lambda y, and 4z cubed has to be 2 lambda z. Okay. All right. So let's think about this restriction, x squared plus y squared plus z squared equals 1. Right? So based on this, what restrictions are there on x, y, and z? All right. Can you all see any off the top of your head? Perfect, yeah. So they can't all be 0. Could 1 be 0? Well, could one of the variables be 0? 1 can't be 0, let's be honest. But can one of the variables be 0? All right. Can 2 of them be 0? Can 3 of them be 0? No. Can none of them be 0? Yeah, that's possible too. So looks like we've got 3 cases we have to think about here, right? One is, what if none are 0? right? So we'll set that up and get all those critical points. 1 could be 0, and then 2 of them could be 0. Right? So these kind of the 3 cases we have to walk through here to get all these different critical points. Right? So let's go through this first one. Right? So let's say none are 0, right? Which means x is not 0, y is not 0, and z is not 0. Okay. So in this particular case, if we look at these equations we got, this system we got from the gradient portion, why or how can I use that piece of information to help solving this particular system? If none of them are 0, how could I simplify every one of these equations? Well, if none of them are 0, then I can divide by x's, y's, or z's, right? Because if x could equal 0, then I could not do this step, right? Oops, that should be equals, right? Because what I want to do is divide both sides by an x to get this, right? But if x equals 0, what's the problem with this particular step? What am I dividing by? Yeah, I'm dividing by 0, right? I'm doing something which is undefined, right? So it's actually pretty important that x can't be 0 here, right? So I can do that particular step. All right, so let me kind of write it up here a little bit closer. And same thing with the y's and the z's. Since y is not 0, I can divide both sides by y. And since z is not 0, I can divide both sides by z. And then I could actually divide both sides by a 2 to get this. And now once we get to this stage, I know that they all equal lambda, so that says that, oh, that should be a squared right there, that 2x squared equals 2y squared equals 2z squared. And if I divide everything through by a 2, I get this. All right. Now remember, our critical points are based on the restriction that we have in this problem. Because we talked before, if we just look at f with no restrictions, then we can get an absolute min, but not an absolute max. Right? So when we're trying to find these critical points, we have to do this with that restriction in mind. Right? So in other words, the critical points have to come from this particular equation. Okay? Now for this one, since x squared equals y squared equals z squared, what I could do is I could take y squared and rewrite it as x squared, and then take z squared and rewrite it as x squared. Right? So this becomes x squared plus x squared plus x squared equals 1, or 3x squared equals 1. So x squared is 1/3, which says if I take the square root, I get plus or minus 1 over the square root of 3. Okay. All right. And in this particular case, remember x squared equals y squared equals z squared, right? Which means x and y and z are all going to be the same value. So for my critical points, I'm going to get plus or minus 1 over the square root of 3, plus or minus 1 over the square root of 3, and plus or minus 1 over the square root of 3. Right. So if you kind of multiply those things out, that gives me 8 possible critical points that we have to check. Okay. All right, so from case 1, these are the critical points that we have. Okay. All right, so any questions with how we found those? Okay. All right, let's move on to the next case then, where maybe one of them is going to equal 0. So let me copy some of this stuff. Yeah. All right, so let me come back over here. So now we're in case 2 where one variable is 0. Right? And to get us going, let's just set x equal to 0, and then we'll worry about y and z here in just a second. Right? So if x equals 0, if you look at this first equation we've got here, that just gives me 0 equals 0, so that doesn't help me out a whole lot. But I've still got 4y cubed equals 2 lambda y, and 4z cubed equals 2 lambda z. And in this case, remember I said one of the variables is 0, so I picked x to be that one for now, which means y and z aren't 0. So what I could do is I could divide this one by y on both sides, divide that one by z on both sides, and then divide both of them by 2 again to give me lambda equals 2y squared and lambda equals 2z squared, which means y squared equals z squared. So let's go back to our restriction, g. I know that x squared plus y squared plus z squared has to equal 1. I picked x to be 0, so that cuts it down to y squared plus z squared has to be 1. And I know that y squared equals z squared, so I could write this as y squared plus y squared equals 1. So 2y squared is 1, y squared is 1/2, so y is plus or minus 1 over the square root of 2. Okay. So as far as critical points go, we let x be 0, y is plus or minus 1 over the square root of 2, and since y squared equals z squared, we'll get the same thing for this one. Okay. Now, that's the case where x equals 0. What do you think is going to change if I look at the next part where I say let y be 0? What type of critical points are we going to get here? Well, y is not going to be 0, but we'd get the exact same work for x and for z. And then if I let z be 0, I would get these values for x and y and 0 for z. So in this case, I get 4, 8, I get 12 different critical points here from this particular case. All right, so you all good with that particular case where we let one of the variables be 0? Now we'll take the dulled silence as a sure. Okay. All right, now the third case was this. Whoops, let me see here. And let me write this up here again. All right, so case 3 that we had here is that 2 of the variables are 0. Don't really need that. Okay, so in this case, let's say x and y are both 0. So if we go back to what we got from the gradient portion, we'll get 0 equals 0, 0 equals 0, and 4z cubed equals 2 lambda z. And since I know, again, z is not 0, I get 2z squared equals lambda. All right. But regardless, go back to the restriction. X squared plus y squared plus z squared equals 1. If x is 0 and y is 0, we're just going to get z squared equals 1, which means z is plus or minus 1. Right. So in this case, for critical points, I get x is 0, y is 0, and z is plus or minus 1. Right. And then we've got the other things we can think about. If x is 0 and z is 0, then y will be plus or minus 1. Or if y is 0 and z is 0, then x is plus or minus 1. All right. So here are the critical points from this particular case. All right. So any questions with how we found those particular critical points? All right. So let's see if we can put all this stuff together. All right. So let me again put this stuff up here. And then let me go back and get these critical points for us. Yeah. And let me go back to here, get these. And let me get these last ones. Those right there, maybe. That kind of fits. Okay. All right. So now what we're going to do to find our absolute max and absolute min is take all these critical points and plug them into my function f. Right. Luckily, with that x to the fourth, y to the fourth, and z to the fourth, these pluses and minuses don't really mean anything, right? So for this first set, when I plug in all of these values, we're going to get the same answer every single time. Right. So if I take x and raise that to the fourth, I get 1 over 9. And then same thing for all of these. So I get the function value of 1/3. Okay. And then for the second set of critical points here, plus or minus 1 over the square root of 2, plus or minus 1 over the square root of 2. If you plug those in there, you get 0 plus 1 over 4 plus 1 over 4. Right? And if you take all of those different combinations and plug them in there, you get the exact same thing, which is just 1/2. And then the last ones, right, that came with the plus or minus 1s on there, you get 0 plus 0 plus 1, which is 1. Right? So here is the biggest output, so that's my maximum. And here is the smallest output, so that's my minimum. Okay. I don't know about you all. I've forgotten how much fun those are. Yeah. All right, so any questions on 11.8 number 10? All right, so again, go back and start looking at that those first 5 standards. See how well you do with those. On Wednesday, maybe we can look at, how about like M1 through M5, right? So for, tonight, start looking at VF1 through VF5, and then for Wednesday, we'll look at M1 through M5, right? And then on Friday, we'll review M6 through M9 as well as VC1, that last one we did. All right. So that's our plan. So just go through there, do some problems, and again, feel free to look me up if you need some help with these things, right? Don't just start reviewing them and think, I don't remember any of this stuff, I can't do it. Let me know how I can help you all out.